All right, welcome back. We're going to go into convolutional neural networks, also known as CNNs. Before we get started, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. So, convolutional neural networks are deep learning models that excel at detecting spatial hierarchies in data, inspired by how the visual cortex processes information. CNN scan data through overlapping local receptive fields, identifying low-level patterns like edges, combining them into shapes, and ultimately recognizing complex objects or signals. Unlike traditional feed-forward neural networks, CNNs are feature, location, invariant. They detect important features regardless of where they appear in the input. This spatial awareness makes them particularly powerful for image analysis, though their applications extend far beyond vision tasks. So, how does this apply across domains? Right? All right. So CNNs are renowned for image recognition. They process many data types effectively. In natural language processing, they perform sentiment analysis and phrase detection using 1D convolutions. Audio and speech applications use CNNs to analyze spectrograms. Medical imaging relies on CNNs for detecting tumors in MRIs and X-rays. Autonomous vehicles use CNNs for real-time traffic sign and object detection. Though transformers have surpassed CNNs in some NLP tasks, CNNs remain computationally efficient for many applications. So, CNN architecture. Okay, so CNNs operate through stacked layers, each serving a specific purpose. Conv2D, so CONV 2D layers extract local patterns using convolutional filters that slide across the input. Max pooling 2D layers downsample data by selecting maximum values over regions, reducing spatial dimensions while preserving important features. Dropout layers prevent overfitting by randomly disabling neurons during training. Flattened layers convert multidimensional data into one-dimensional vectors. Dense layers perform fully connected neural processing for decision making. Softmax layers convert final outputs into class probabilities. So these layers typically form a pipeline. Conv 2D, max pooling 2D, then to dropout, then to flatten, then to dense, then to softmax. So, for example, a color image, let's say it's 128 by 128 by 3, might reduce down to 32 by 32 by 32, right? After convolution and pooling, it might flatten to 32,000 features and then pass through dense layers and softmax for classification. So let's see an architecture here, right? So this would be a good example of one, right? So several proven architectures provide starting points for CNN development, okay? LeNet, LeNet -5 is a simple CNN designed for digit recognition on small grayscale images like MNIST. AlexNet introduced deep networks using ReLU activation and dropout for image classification on datasets like CIFAR, which is CIFAR, FAR. GoogleNet uses inception modules for efficient large-scale image recognition. ResNet employs skip connections that preserve gradient flow in very deep networks, supporting architectures from 50 to 152 layers. So ResNet is particularly important in AWS SageMaker. It's a default option in JumpStart for image classification tasks. The skip connections solve vanishing gradient problems that plague extremely deep networks. So how does CNN integrate in the AWS services? SageMaker JumpStart that offers pre-built CNN models like ResNet 50 for image classification. SageMaker Studio notebooks let you customize CNNs using Keras or PyTorch. And then Amazon Rekognition can use CNNs behind the scenes for face detection, object recognition, and PPE detection, right? So Amazon Lookout can use this for vision and applies CNNs based on anomaly detection in industrial images. All right, so let's go into the console. All right, so you're going to be in SageMaker. JumpStart right here. All right. Oh, this is going to take. All right. So let's see. Would it be NLP models? Yeah. There we go. All right. So here's two options. Okay. So you would open this, open in the studio. Right. And this will create a whole environment. And you can review the notebook, configure your data, train the model. All right. So a couple of things to know. Let me see. All right. Once you get this provided endpoint, you can invoke predictions on your images, and your model can return class probabilities showing the confidence in each possible classification. So CNNs are computationally expensive, right? So this is especially true with large images or deep architectures or extensive hyperparameter tuning, right? So the GPU-backed instances are especially essential for CNN training. So that ml.p or ml.g, those instance types, right? And the training time can depend on a lot of things. You can do it continuously, or you can do it in batch. But you have to mind your batch size, your learning rate, and your data set size. An S3 can cost a lot for data set storage. Also, EBS volumes add charges for notebook instances. So those deployed endpoints with all those previous things mentioned can multiply your costs. All right. So a couple things to go forward. All right. So for the exam, remember a couple of things. CNNs excel at detecting hierarchies and feature location invariance. Two, standard architecture has a flow. Conv to D, max pooling, dropout, flatten, dense, softmax. Basically, when an exam is asking about image classification, spatial feature detection, or choosing architectures for computer vision tasks, CNN, particularly ResNet variants available in SageMaker, is your answer. All right. Thank you for joining. Have a good day. But before you go, hit the like, subscribe, and share with anyone you know taking the AWS Machine Learning Associate exam. Have a good day.